Hi everybody, my name is Natalie Boyd and I am a math teacher at Hume Fogg Academic Magnet in Nashville, Tennessee. Today I wanted to talk to you a little bit about what a radian is, how you can convert from radians to degrees and then degrees to radians, and then also what the key radians are around the circle. This lesson is hopefully leading you into learning about the unit circle. So let's talk about what a radian is. It's another way of measuring an angle, just like a degree is a way of measuring an angle. Only the degree is actually a little arbitrary. The Babylonians thought that there were 360 days in a year, and so they just divided a circle into 360 tiny parts to make degrees. I know that everybody is used to using degrees, but radians are actually super, super helpful, and they actually make a lot of sense. And you'll find that when you move to pre-calculus, you will be working with radians almost exclusively, and then definitely you'll be using them in calculus. All right, so let's talk about it. What is a radian? I'm going to draw a picture here and kind of show you a couple things. So let's suppose that we have this circle here that has a radius of r. If I was to take that radius, the length of that radius, and then like lay it down on the circle, we'll do our best. I'm just sketching. We'll pretend that that's the same length as r, okay? So there's a piece of string laid on the circle that's the length of r. The angle that is made by that, like the angle that creates that arc, is going to have a measure of 1 radian. So theta would equal 1 radian. We're used to degrees, but that actually is a certain amount of degrees. So let's figure out what that is and let's talk about it. If 1 radian is made when the arc length is the same as the radius, that's like this ratio right here. A radian is basically a ratio. So the radius divided by the radius is 1. So if I wanted to find how many radians fit in this much of the circle, I would need to find like how long that is, however long that is, and divide it by r, and that would give me the number of radians. Okay, I promise this will make sense eventually. Hang with me. So arc length, however long the arc is, divided by the radius, tells you how many radians that angle is. All right, so I want you to think about something. Let's think about the entire circle. What if I wanted to go all the way around the entire circle? We know how long that is. We could figure that out, right? So I'm going to just draw. I know this is a little sloppy, but let's say I take the red, going all the way around. If I wanted to know how long that red is, I would need to find the circumference, right? So my arc length would be the same thing as the circumference. 2 pi r is our circumference. So following my little formula up here, arc length over radius equals radians, I would do 2 pi r, that's my arc length, divided by the radius to figure out how many radians there are in a whole circle. Well, notice it doesn't actually matter what my radius is, and this is part of why radians are so great, because you can use them no matter how big or small the circle is. It's all proportional. Notice that my r's are going to cancel in this formula, and I'm just going to get 2 pi. So that means that there's 2 pi radians in a circle, in a whole circle. Okay. How many degrees are there in a circle? 360, right? We talked about that already. So 360 degrees equals 2 pi radians. All right, I want to talk about a couple of things that sometimes cause a misconception. The pi is not a unit. It's not like inches or something. Pi is a number. Pi is always a number. It is 3.1415926 something, 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 right? Pi is a number. So when I say that there's 2 pi radians in a circle, I'm saying that there's about 6.28 radians in a circle. If we go back to that idea of taking a piece of string and laying it down on top of the circle, that means that I could lay a piece of string that's the size of a radius down on the circle, and it would fit about 6 of them. 6 and a little bit more would fit going all the way around the circle. Let's talk about how we can change radians to degrees. We need to use this idea right here. So let's talk about that. Earlier we said that 2 pi radians equals 360 degrees. We can do a lot with this. This is going to be a key thing. I think if you can remember that there's 2 pi radians in a circle, you can pretty much figure any of this stuff out. If I wanted to figure out how many degrees were in 1 radian, I would need to divide both sides by 2 pi, since 2 pi divided by 2 pi is 1. And it turns out, exactly that's 180 over pi. If I wanted to know approximately, it's 57 point something. That's less helpful. What's more helpful is this 180 over pi thing. I also can go the other way. If I know that 2 pi radians are the same thing as 360 degrees, then that means that I could divide both sides by 360 if I wanted to end up with 1 degree, and 2 pi over 360, if I just reduce that, that's going to give me pi over 180. Okay, so there's pi over 180 radians in 1 degree. There's lots of different ways we can use this. I think some people like using this as a unit conversion, kind of like there's 12 inches in a foot. You could use it that way. You can also use proportions. I've had a lot of students enjoy doing these kind of problems using proportions. So let's talk about that. If I wanted to use this with proportions, one thing that you're going to have to be able to do in pre-calculus and also here at the end of IM3 is convert from radians to degrees and degrees to radians. So let's do a few examples. If I have 60 degrees, I'm going to do some of the common ones. So if I have 60 degrees and I want to change that into radians, I'm going to do this in more than one way. So one way would be to use the unit conversion way. I'm going to multiply by pi over 180. And the reason I know I need to do that instead of the other way around, 180 over pi, is that the 180 is the degrees. I want my degrees to cancel out. There are pi radians and 180 degrees. If I multiply straight across, I get 60 pi over 180. And you basically just have to reduce your fractions. So I can divide by 10. And 6 over 18 is the same thing as 1/3. I divide both of those by 3. So the common way of writing radians is like pi over something. So 60 degrees is the same thing as pi over 3. I've had some students in the past who prefer to do some kind of proportion, let's say. So they would be like 60 degrees out of 360 degrees is x radians out of 2 pi radians, because they know that there's 2 pi radians in a whole circle and there's 360 degrees in a whole circle. If I cross multiply, I get 360 x equals 120 pi, and I would have to divide by 360 on both sides. And that actually also gives me pi over 3. So we've established that 60 degrees is pi over 3. I'll do a couple more just so you can see a couple examples. Let's do 30 degrees. So I'm going to do the first way that I showed. 30 degrees times pi over 180. My degrees cancel out. I get 30 pi over 180. And then I can simplify my fraction. So I'm going to divide by 10 on both sides, or on the top and bottom rather. I have 3 pi over 18. 3 goes into 18 6 times. So that's pi over 6. Okay, these are going to come back later. So I'm showing them to you now so that way you can, they'll be somewhat familiar. Okay, let's do one more. Let's do 45 degrees. I'm doing relatively small ones right now, but you can do anything. Notice the conversion factor is the same every time. This one might be a little bit trickier, but you could get a calculator out if you wanted to and see what 45 over 180 is, or you could do 180 divided by 45, but 45 goes into 184 times. So this simplifies to pi over 4. Let me do a couple quick examples of the other way. All of those were degrees changing into radians. But what if I gave you radians and I wanted you to change it into degrees? So suppose I have pi over 2 radians. Radians are kind of strange because they are a ratio. They don't actually have units. So there's not like a term that you write next to it, like a little degree symbol. It's just kind of pi over 2. So we have pi over 2 radians. This time, I want to convert 2 degrees. So I'm actually going to cancel out the pi's because I have a pi on the top and a pi on the bottom, and I multiplied by 180 over pi. So notice how these two problems are different. Number 3, I multiplied by pi over 180, and in number 4, I multiplied by 180 over pi. It just depends on what you have and what you're trying to get. So I had radians and I'm trying to get degrees. So I don't want degrees to cancel out. I want them to stay on the top. Pi is a number, but I happen to have it on the top and the bottom. So those do cancel out. And I end up with 180 divided by 2, which is 90 degrees. Do one more. Let's do 2 pi over 3. So because I'm starting with radians again, I'm going to multiply by 180 over pi. And my pi's end up dividing. And I can simplify this. I can do 2/3 times 180, or I could do 2 times 180 across the top and then divide by 3. I could do 180 divided by 3. I kind of feel like doing if I do 180 divided by 3, that gives me 60. And then 2 times 60 is 120. Okay, so now I've done all the converting. Let's talk about why this is helpful for the unit circle. Maybe you've seen this kind of picture before. This is just a circle that's divided up into pieces. I think it's easiest to look at this in different fractions. So we're going to just look at different fractions going all the way around. I'm going to do some highlighting here. For the first one, let's talk about just these angles that I've highlighted in red. So we know, back to the very beginning, how many radians are in a whole circle? 2 pi. So if I were to go all the way around like that, we always start with the x-axis that's positive and move counterclockwise for a positive angle. This is 2 pi radians. So let's think about circles. If all the way around is 2 pi, then half of the way around would be pi. I like to use that fact a lot. You're going to see that in the next pages. So pi is half of the circle. Well, notice that this line here in the middle is cutting pi in half. I'm going to draw a little blue half circle. So there's my half circle. Do you see how the red line in the middle is cutting it in half? And if that half circle is pi, then that means this has to be pi over 2, or half pi. And then I kind of like to count. So I'm going to use another color. I'm going to use green and kind of count, and hopefully you can see what I'm doing. I'm going to start on the x-axis. If I go 1/4 of the way, that's half pi. This is 2/2 pi. This is 3/2 pi. 4/2 pi. So I have pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. So this little guy down here should be 3 pi over 2. And I just wanted to, I'm going to draw the same thing as saying 4 pi over 2. So I'm just going pi over 2, pi over 2, pi over 2, pi over 2, pi over 2. Okay, so that labels those. Those are called the quadrantal angles. Let's look at a different fraction. What if, actually, yeah. Let's look at a different fraction. Let's say I start with these guys again. I know that those are my over 2's. Those are my halves. But what if I cut them in half? Okay, so let's just think in terms of fractions. How many sections are there in that half circle? Let's kind of shade them real quick. So here's a section. Here's a section. Here's a section. And here's a section. So notice there are 4 equal sections in that top half. And we talked before about how this top half is pi radians. Starting at 0, going halfway around is pi. So this line right here is 1/4 of pi. Or most people write that as pi over 4. And then this one is 2/4 pi, which is the same thing as half of a pi. This one must be 3/4 pi. And then this one is 4/4 pi, which is the same thing as pi. Now the thing that's nice about these is you can just keep counting. So I have pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So then of course that means the next one down here is going to be 5 pi over 4, 6 pi over 4, 7 pi over 4. And notice that 6 pi over 4 is the same thing as 3 pi over 2. Okay, I have all the pi over 4s labeled. So now I need to go to the thirds or the sixths. There's different ways to look at it. Okay, so this time, let's start with the pi. And then these are a little bit harder to see. If I cut this into thirds, do you see how I have 3 equal sections? I just cut a half circle into 3 equal sections. And then I could follow that down here. I could cut those into 3 equal sections. You can see 1, 2, 3. So I have 3 sections there. Let's label these. I know this is 0. I know this is pi. The first blue section is 1/3 of pi. So that's going to be pi over 3. This one will be 2 pi over 3. Pi is the same thing as saying 3 pi over 3. So pi over 3, 2 pi over 3, 3 pi over 3. That means the next one down here is going to be 4 pi over 3. And then the next one is 5 pi over 3. And then I have 6 pi over 3, which is the same thing as 2 pi. So in black, I have now labeled all of my pi over 3 sections. Notice there's a lot of overlap. So everything we've done so far has overlapped on the pi and the 2 pi, but it's also, some of them have overlapped on the middle ones too. This one didn't. Okay, we have one more to do. One more section that we haven't talked about yet. And that is the sixes. So it was that line. I'm going to start here again. And then notice I'm skipping the one in the middle. And I have just split up this half circle into 6 equal parts. There they are. And then I can keep on going. Okay, so there's 12 total, but the top half is cut into 6 pieces. So that means that this one's 0. Switch to my pen real quick. This one's 0. This one's pi. So the first little tiny section is 1/6 of pi, which is pi over 6. That means this next one will be 2 pi over 6. I'm going to do some reducing of fractions in a minute, but I'm going to keep going for now. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, same thing as pi, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. Now notice a lot of these can reduce. So obviously 12 pi over 6 is the same thing as 2 pi, because 12 divided by 6 is 2. Also, 2 pi over 6 can be divided by 2 on the top and the bottom to get pi over 3. We just showed that on the last page. This is the same as pi over 2. Here is 2 pi over 3. And 5 pi over 6 can't be reduced. There's pi. 7 pi over 6 can't be reduced. 8 pi over 6, both of those could be divided by 2, so you get 4 pi over 3. With 9 pi over 6, both of those can be divided by 3, so you get 3 pi over 2, which we showed at the very first one. And both of 10 pi over 6 can be divided by 2, so that's 5 pi over 3. So you can kind of see how the pi over 6s and the pi over 3s overlap. I know this might seem like a lot, but the good news is there's a great pattern you can follow. And you can just always make sure, like you're eventually going to need to memorize this, probably in pre-calculus. So it might be helpful to go ahead and do that now. So I'm going to copy this real quick so that we have another page. Okay, so notice what I'm going to do is I'm going to overlap these now. There's the pi over 2s, then we have the pi over 4s, the pi over 3s, pi over 6s, and then we can put it all together. While I'm writing these down, I want you to notice if you see any patterns. Oops, I've already messed up. This one was pi over 4. And they're not really going on the dots. They really are going on the line. So like pi over 6 is the measure of that angle right there, for example. 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, and then we have 5 pi over 3, 7 pi over 4, and 11 pi over 6, and 2 pi. There you go. Those are all of the angles, like the key radians going around the circle. Now, I do want to point out a couple of patterns to you. So hopefully you've noticed that there's a pattern about the denominators. So do you notice that these ones that I'm highlighting in red, they all have a 6 in the denominator? And these ones that I'm highlighting in blue all have a 4 in the denominator. These green ones have a 3 in the denominator. And then these that I'm kind of doing in a gray, these kind of have 2s in the denominator, but of course the pi and the 2 pi are reduced. So now that you kind of see the pattern in the denominators, let's take a look at the numerators. This should be really helpful. I know this is getting long, but hopefully this will be helpful. All of the numerators in the first quadrant are just 1. They'll have a numerator of 1. Numerator equals 1. But all of the numerators in this second quadrant, look at the numerator compared to the denominator. They're all 1 less. So the numerator is the denominator minus 1. So if you can remember where the denominators go, then you can remember just to do minus 1 there. These ones are all the denominator plus 1. Okay, and then this last quadrant is a little bit trickier. They definitely are related. If you multiply the denominator by 2 and subtract 1, it works. So the numerator equals the denominator times 2 minus 1. Now, that pattern is really helpful for memorizing, but I don't necessarily recommend only memorizing. It's good to understand where these come from, and I'm hoping that this video helped you see where they come from. They're basically just fractions of a circle. So it would not be a bad idea for you to make sure that you memorize this, or that you use it, or at least that you're comfortable with it in Integrated Math 3. When you get to pre-calculus, this will probably be one of the first things you learn, and you will definitely be ahead if you already understand it or already have it memorized. So best of luck to you, and I hope you found this helpful.